Kubernetes or have it in production? Great, a whole bunch of people. Oh, excellent. How many of you guys have heard of stateful sets or have used one? Wonderful, excellent. So I think we're all set. Okay, so before we go into that, maybe a quick intro about us. So I'm Karthik. I think Oliver before set the stage pretty well. He talked about Twitter, the scaling pains, microservices, or the lack of the term back then. So at the same time, I was at Facebook, saw the journey at Facebook. It wasn't very different, to be honest. Like, we were thinking we were going to be this week, and we thought that every week, and we thought that for many, many weeks until we really crawled out of it, right? Like, it takes some effort, right? And like, I'm one of the co-founders, and my other two co-founders, along with a whole bunch of people in our team, we worked on the database side of Facebook during this period, during the period that they went from pre-cloud native microservices type architecture to a post architecture, which really held for a lot of requests, you know, all the goodness. And that's where we learned, learned planet scale and what are the challenges with the data tier and so on and so forth. So we're about like 25 people now, a lot of us from modern web companies, Facebook, Nutanix, Google, LinkedIn, so on and so forth. We've built a whole bunch of apps on top of NoSQL platforms. Like I've worked on Cassandra before it was called Cassandra, before it was open sourced, way back when, before NoSQL was a thing. Worked on HBase with a whole bunch of people. We put it in production for some very large use cases, including Facebook Messages search, our operational data tier, which did alerting and metrics, and spam detection, and a whole bunch of others, right? So our current company is a distillation of all of that. But before we go into what we do now, right, wanted to quickly talk about how do people build planet scale apps, right? The Docker plus Kubernetes ecosystem, it's great for the stateless tier. It's very intent-based, really easy to deploy, a lot of great tools, and that's pretty much where everyone is headed. But how do you deal with the data tier? How does that look? And of course, we're talking about the era where public clouds have become mainstay. There's like 70, 80, 90 data centers available to you. I just have 2 data centers is no longer an excuse, and your users don't really care. They want their answers quickly. If not, they're going to the next app, right? Or Amazon will come get you, depending on your field. So, okay, how do people do this? Well, typically there's a sharded SQL master slave for the most critical data. And then there's one or more NoSQL tiers for depending on your velocity of data, density of data, type of access pattern, et cetera, et cetera. So you now put your data across these tiers. And because you have your data in so many tiers, you now need to bring what the user wants into something that can serve it really fast, right? So now begins the fun dance, like figure out which pieces of data go where, figure out which pieces of data go into the cache because the user cares about them and the user's behavior constantly changes, so your cache has to adapt. Now figure out how to replicate each of those tiers. And finally, of course, there are going to be failures in this sort of a thing. Figure out what went wrong and how, right? And do it quickly. And keep changing stuff, changing machine types, changing data centers, keep doing all of this. Well, you'll get a generous 3 months to 6 months to do that, but it's a full-time effort from the app team, the ops team, the database team, everybody, right? And we've seen the story play over again and again. Okay, so Amazon should solve that. The public cloud should solve that. Well, not really, right? So let's see how it really works. If you take AWS as an example, you have Elasticache that takes care of Redis, so you don't need to deal with the machines. You have Aurora or an RDS that takes care of your SQL tier, but it's essentially the same architecture underneath. And you have DynamoDB, which replaces the NoSQL tier, right? So you've taken care of the machines and the patching, but the app complexity and the complexity of running the system with data integrity and production, still the same. Same thing, right? So what did we want to do at Yugabyte? Well, we just thought we'd solve world hunger and put it all in a single database. Well, of course, I'm joking, right? So there are certain trade-offs that you have to make when you're trying to build scale-out applications in a cloud, right? So we've made those trade-offs, and we've seen what it takes to put a database for a variety of different workloads and what are the common asks, right? And so that's what we're going to be looking at. Okay, so what are your choices really, right? And where's the world evolving? How do you make sense of this space? If you want a strongly consistent database to build global applications, what are really your choices? You have the traditional SQL databases, but they're really not scale out and they don't really do planet scale. You wouldn't be able to deploy your data across different data centers, scale out when you need to add a whole bunch of machines because you need to serve more queries or store more data, et cetera, et cetera. So the NoSQL guys came up with a solution. We'll take care of the scale out, right? They gave up on transactions. They said, we'll be high performant and we'll do scale out. But there's still that 20, 30% of your workload that needs transactional guarantees. And what do you have to do for it? You need another database, which then brings in a cache and you're back where you started, right? So databases like Spanner took another tack. They said, we're going to push SQL to its limit. We're going to take it to the bleeding edge, right? So they give you transactions. They give you scale out, but they're not the database you would go to if you want to write a lot of data or serve them really, really quickly. So performance is what they gave up on. So what are we doing here at Yugabyte? We're trying to bring in the best of both worlds into a single database. So if you want to distribute your data across the planet, if you want to do it serve your data with high performance, so if you just want a unified integrated serving tier, and if you want the ability to do transactions, whether it's single row ACID or multi-row ACID, like distributed transactions, both, we wanted to make a single data platform because we think that the apps of the future are going to increasingly look like this. Okay, so we started to build this database. What were our design goals? Transactional, high performance, planet scale, right, at the core database layer, and cloud native and open source. So on the transactional side, we built a data platform that understands single row versus multi-row distributed and keeps the single row extremely fast and the multi-row extremely consistent. On the high performance side, we didn't go Java, totally with Oliver. We went C++ actually, because C++ is still the language to go to if you want extremely high performance, so ground up written in C++. For data, for planet scale, we have the ability to distribute data across to various regions, like far and near, and we can support reads from nearby data centers so that you can achieve low latency reads while being able to write from anywhere and maintain consistency. And of course, at the core of the database is automatic sharding and rebalancing. So you don't have to think about sharding or rebalancing. The database does that for you. On the cloud native side, it's all built for the cloud and the container era. So it makes it very easy to deploy, run, and manage. And it's self-healing and fault tolerant. So if there are any failures, and there's a lot of failures in the cloud, you don't have to wake up at 3 a.m. to go figure out what was wrong with your database. And believe me, we've done that as a team many times. You don't want to do it. Or some of you may already know that. So, and the self-healing nature is that you will still respect the user's promise, if possible, of how many faults you can tolerate, right? As long as it is possible. We're an Apache 2.0 project. You can check us out on GitHub. And we started out not only being open source, but also with open APIs, which means you don't have to learn a new language, right? We're a multi-model database, and we're going to look at what APIs we support. We support Cassandra query language, Redis, and we're working on Postgres, so it's well-known languages. All right, so what were our core database goals, right? We wanted to be very similar to Google Spanner in the core. So in terms of the CAP theorem, we're a consistent and partition-tolerant database, a CP database, but we can offer HA, right? Isn't that like bending laws of physics? Well, no, not really, because what we give up is just a few seconds of availability. So on a failure, we're able to re-elect a master and a leader in just a matter of a few seconds. And so you will be able to get your HA, right? And there's another way to look at it, which is this, the Pace-LC theorem. But anyway, the short of it is you can get all the three elements in the CAP theorem: consistency, availability, and partition tolerance, as long as you don't hit failures. The trouble really starts when you hit a failure. And when you hit a failure, Yugabyte trades off latency for consistency, because it takes a little bit of time for a new leader to get elected. And at the core of the database, it's a document model. It can support SQL-like APIs on top. It has distributed transactions, but is single-row transactional by default. And it also has the ability to support a native JSON data type, like a lot of SQL, MongoDB type databases. Okay, on the API side, we started with well-known APIs because some of these APIs are really good for modeling distributed systems. So we started with a Cassandra query language, which knows about how to partition data across nodes, or knows about when you add a new node, how can you go and read data, the subset of data that new node now contains with very, very low latency, right? Or a Redis-like API, which is really good at modeling data structures, except this Redis is a full-blown database. You don't have to worry about persisting your data elsewhere, right? And we're working on Postgres. Now, on Postgres, we have to teach Postgres how to split data across nodes, or how to make the driver aware of multiple nodes to give performance out of a multi-node system, right? So those are things that we're working on. Yeah, so the core of the database, irrespective of which API you use, contains the same set of features. So you can do tunable read consistency from all of these APIs, which means you can read from your nearest data center and get a cache-like experience, or go read it from the actual leader and use it like a database. It's write optimized for large data sets, so we do streaming ingest really, really well. So batch reads and writes are pretty good. Data expiry with time to live, that the database supports it. Like most SQL databases do not have this. NoSQL databases do, but that's something we have retained from the NoSQL side. And it's a single operational runbook across all these APIs, right? So it makes it very simple when you run this in production. So to summarize, right, if you think of Cosmos DB as the bleeding edge of NoSQL today, and Spanner as the bleeding edge of SQL, we're bringing the best of the two worlds into a single system. Okay, very, very high level, quick architecture. Like, I'm hoping you guys will ask me questions if something is not clear. At the core, it's a scale-out system. So you just take a whole bunch of commodity machines or containers and put them together, and the database now recognizes it and presents itself as a coherent whole. Each of these nodes or pods contains a document store, which is a heavily extended and modified version of RocksDB that works well with a Raft-based replication engine. The Raft-based engine is needed to keep consistency of data across different nodes, on top of which we have a global transaction manager, right? So now this entire thing comes with automatic sharding and load balancing. So you don't have to worry about what happens when I add another node or when I remove a node, right? It can automatically shard and load balance itself. And finally, on top of everything, you can access the database using your well-known APIs. And obviously, we have been extending these APIs, so you can still interact with them with the open source drivers, but we have additional things, like we have extended Cassandra to add a begin transaction, end transaction type semantics to do distributed transactions, which Cassandra does not support, or JSON data type, and so on and so forth. So for those, you will need to use our drivers, but they are in the open source as well.
So you have the leader selection based on a Raft protocol.
That's right. So the question was, the leader election, is it based on the Raft protocol? Yes, the leader election is based on the Raft protocol for each chunk of data. Each chunk of data is called a tablet. Each of the tablets form a Raft group, and they elect their own leaders.
So how do they decide the tablet?
I'm sorry?
How the tablet will divide the tablet?
The tablet is uniform partitioning of the key space. So you take the entire key space, and we chunk them up into a lot of small tablets. Each node hosts some set of tablets. The tablets have replicas that go across multiple nodes depending on the replication factor. Each tablet with its peers will elect a leader, and they're a completely independent unit. It doesn't depend on there has no external dependency, so no zookeeper, nothing. It will do its leader election by itself inside.
So then join the table don't cross tablet.
I'm sorry?
If a two table has a relationship, but it don't cross tablet.
If two, repeat the question. Yeah, I'll repeat it. Yeah, sorry. Yeah.
If a two data set, right, have a relationship,
yeah,
how to put it into one tablet, right?
So yeah, great question. So if two sets of data have a relationship, the question was, do you put them into the same tablet? If they're in different tables, no, we do not. They're in different sets of tablets. However, we allow these tablets to be co-located on the same machine. This is a feature that we are working on. It's in our roadmap. We call them co-partition tables. So these tables are co-located, right, and split the same way. Okay? Yeah, so it turns out that distributed transactions is really like a whole bunch of tricks if you want performance out of it. So this is one of them, actually, and that's a great point. Okay, so all of this runs on top of any IaaS, so no external dependencies, just needs memory, CPU, and disk, and it can go forth and do its thing. And because of the API compatibility, it's very well integrated with the ecosystem. So it works, Spark works on top of the database. So you can use a Kairos DB for a time series data, or a Janus Graph as a graph database, or a Spring Boot type ecosystem to build apps on top. So it's really easy. Yeah, please, question? Yeah.
I'm curious about the latency if the nodes in this diagram are geo-distributed, right? In the planet scale, I can see how reads are fast, but what about writes?
Yeah, great question. So writes follow laws of physics. By the way, I think you guys are asking great questions. I'm supposed to be giving you stickers, and I forgot. But anyway, you know, who remembers with good questions, right? So yeah, so it follows the laws of physics. Your writes, if you're trying to achieve consistency across faraway geographies, are going to take a longer time. There's just nothing to do to get around that. But one of the things that we have is we've extended Raft to have an observer node, like for an async replica. So you can have a read-only replica that's placed far away, or an async replication pipeline that will not incur write latency. So you'll be able to easily design it as one set of machines are geographically relatively close and offer you strong consistency, while you place a whole bunch of replicas that are far away, which will still get the writes in timeline consistent fashion, not eventually consistent, it'll be timeline consistent, and you'll be able to serve data from there. You'll be able to write data there as well. It'll like redirect it to the right place and get the data written. So I think there was another question, or maybe not. Yeah, please, yeah. Yeah, stateful sets, I'm getting to that. So I'm just telling you so the question was, how does it work with stateful sets? And yeah, we'll get to that. So, all right, so I'll quickly go through where we are with the project. 0.9 beta version publicly available on GitHub. You guys can try it out on your laptop. You can try the various scenarios. Like, you know, it's pretty easy to do that. We've stress tested it up to like 50 nodes. We could keep going higher. We're very comfortable as a team running hundreds of nodes in a cluster because we did that at Facebook. The same design goes in here. What you'll notice is even at 50 nodes, we don't give up our low read latencies. Our read latencies are in the hundreds of microseconds, depending for a simple key value type read. So in this case, we're doing like 2.6 million reads at 200 microseconds and 1.2 million writes in a 50-node cluster at like just 3 milliseconds write, but this is a 3-way replicated consistent write, right? So it's like it can survive a failure. It's a really high performance. We've tested it with YCSB as well. A lot of people asked us, like, if you're doing consistency, what are you giving up? How much performance are you giving up? Well, it turns out if you architect it right and you go all the way down to the bottom, like all the way to how the data is being replicated or how it's being written, you can actually get very, very good performance out of the system. So these are our YCSB benchmark results. We've written a blog post about how is it that we can make our system have high performance along with consistency. You guys can check it out, blog.yugabyte.com. We support distributed ACID. So on top is a classical bank accounts kind of table. There's a row which is an account name, another row which is an account type, and a third row which is a balance, which is the total. The interesting thing with a Cassandra query language is it'll tell you how you can partition your data. It looks very SQL-like, right? But you can partition your data across nodes, right? We want to keep all the data for a single account together, right? So that's what this thing is doing. It is sharding the data by the account ID and keeping all the account types very close on disk. So it's really, really fast, right? And the transaction that's being done below is for a user, John, to transfer $200 from his checking account to a user, Smith, who could like live on, and these guys could live on different nodes. You can do the same thing across different tables. So it's just like your regular transactions, right? And this forms the basis for implementing other things like consistent secondary indexes, which are highly performant and so on and so forth. And these are things we're working on. Okay, so we are deployed in a whole bunch of customers, but this is one of the deployments that people really like. I think this goes to the question that I think you asked. In this setup, it's geo-distributed, 2 copies of the data in US West, 2 copies in US East, and 1 copy in Tokyo. So completely planet scale. This is an example of users logging in and changing their password. So with the application running on all the data centers across the globe, what we find is around 200 microsecond latencies for people trying to log in, and about 200 millisecond latencies for people trying to change their password on average, right? Because your data for consistency really has to travel, right? And in this particular example, it can survive a whole data center failure. So if you think about users logging in and changing their password, slightly higher latency in the order of 200 millis is okay to change password. You have to be absolutely quick to log in. 200 micros does that. You don't need a cache in front, right? So it's multi-cloud, so it works with Amazon, AWS, Google, on-premise, and we're working on Azure. It works with stateful sets, which is what this whole talk is about. But anyway, so the point is it has no dependencies. It's easy to deploy anywhere. All right, so for the demo, we're going to look at Yuga Store, which is a React.js and Node.js Express app. And the app is a shopping cart app, so it's going to be a bookstore type of app, right? And the app itself is on GitHub, so you guys can download it, try it out. Like, you'd need to set up Yugabyte as a stateful set. There's like a whole bunch of instructions there. You guys can check it out. All right, because it's not very interesting to watch all these things get set up. So I've already done these steps and kept the system ready. But effectively, that's the one line that you need to run in order to bring up Yugabyte in a stateful set, right? And the second thing that I did was containerize the application as well. So it's like the standard stack. It's a pretty popular stack. So containerize that and ran the command up there. Again, you can find these commands on the GitHub repo, and brought the app up and running. So let's go take a look at the app. So yeah, before that, this is my deployment on the local host. So it's just showing the Kubernetes dashboard. What you see is this is a 3-node cluster with 3 tablet servers. So it's got 3 nodes, so slaves that do the actual work. Its replication factor is 3, so that's why there are 3 masters. So it's replicated 3 ways and can survive a failure of any one node. And finally, this guy here is the service that's running the stateless application, right? And you can have a whole bunch of them. You can scale them out pretty easily, so on and so forth. And for the actual storage, we use persistent volume claims. So we're mounting the disks into each of the pods of the database, and it uses that to store data. Yugabyte can just work fine with ephemeral local storage as well. Like, just local disk is fine. Okay, so I'm going to go into deployment that I've done on the Google Cloud, right? So this is a GCP GKE install, so Google Kubernetes Engine-based install. I ran the same set of commands after installing the gcloud, like whatever API. What this shows is this is a 4-node cluster replicated 3 ways, right? And these are the masters that form a highly available Raft group, and they keep track of the metadata in the system. There is one table in the system. It's a products table in the Yuga Store key space, right? Like, it's just like if you're familiar with SQL, a key space is like a namespace, and a table just is a table. Okay, so if we go look at the tablet servers, or the slaves that are doing the work, you see that it's all a single cloud, single data, like rack or region, and single availability zone install. So this is not a multi-cloud installation, right? So it's just, but it can very easily become one, right? Like, it's just like easy enough to deploy Yugabyte that way. Okay, so here's the app itself, right? The app is a bookstore app. What it shows is a whole bunch of books with some data. The books are split into categories. Like, there are some static categories, like business books, cookbooks, mystery books, and so on. And there's some dynamic categories, like show me the books with the highest rating, right? Or show me the books that have the most reviews, right? Like, typically what you would expect from a store. Now, how do we build this, right? Like, let me go back here. So the multi-API strategy, it turns out, really, really simplifies this. Because you have Redis as a database that's still highly performant, and Cassandra as a highly consistent and performant database, it's easy to put the less dynamic pieces of data, like the title of the book or the description and so on and so forth, into the Cassandra database, which just looks like an SQL table. Now, on the Redis side, you can put the very, very dynamic pieces of data into Redis. For example, the number of reviews or the total rating, right? All of those go into Redis. So querying for the top books in a category just looks like a SQL query, right? Select star from something where category equals something, right? Whereas you can use a Redis sorted set to keep track of your books sorted by your number of reviews or your ratings, right? So, and that makes it really easy to model the app because you have the right data structures at your fingertips, and you don't have to worry about, now I've put my data in Redis, let me figure out where the backup of that data goes. And if this thing dies and gets replicated elsewhere, how do I serve the data? How does my app need to move data between tiers? All of this is gone. It makes it a lot simpler. So we can go and check this out if I find, yeah. So this, yeah. So I deployed this in GKE just minutes before the talk started. I had a 3-node cluster. I added another node, another pod. I scaled it up to 4. What you see is there are now 4 nodes, right? So, or 4 pods. But
how data layout change if you increase the number of
the data will, I'm actually going to show you. Actually, I'm going to show you with respect to the queries, but the data is split into small shards. The shards are automatically moved across different nodes. So as you add nodes and remove nodes, the shards of data automatically rebalance themselves. So you don't have to worry.
So would I need to pay the balancing cost?
Yes, so question is, if you add nodes, would you need to pay the balancing cost? So in Yugabyte, because it's strongly consistent, we actually copy compressed files. So as the equivalent of that. So the database automatically takes compressed files and copies them over, exactly the subset of files that are moving to the new node. So yes, there's data copy cost, but the data is very efficiently copied. And this does not affect your foreground app, right? So because you're not reading through the database, you're just taking the files. So a database has to read some subset of data from the disk, uncompress it, and then do a whole bunch of reads and resolves on them in order to serve a user query, right? And most typical databases today, like if you take a Cassandra or a MongoDB or most of these databases, if you add a new node, will read almost through the database to resolve the data and then get the data out and copy it into the new node. While with Yugabyte, because of its strongly consistent properties, we can go to the compressed data files and copy them straight, and then have the new node join the replication in the raftering. Right. Exactly, yeah. Please, yeah.
How does one determine where data types are going? Into the high performance tier, the lower performance tier? Does the database decide that? Or?
Database decides that. You don't have to worry about any of that stuff because typically an expectation is that if you enable like distributed transactions, right, you will be subject to clock skew. One of the things that Yugabyte can do, and we're working on it, is to integrate with an external like atomic clock service, like an Amazon's time sync service kind of thing, at which point your distributed transactions are reasonably performant as well. But if your query pattern automatically becomes single row, it automatically starts getting the benefit of high performance. And we do the work to compute at what point a single row ACID conflicts with like a provisional write for a multi-row. We do all of that tracking. Sure. All right. So yeah. So what I was going to show is that you can easily run a query like that, right? And it's gonna, and that's the type of query that you would run to say, hey, give me books in the business category, give me 3 books in the business category, or you could say, give me all the books in the business category that are hardcover books, right? Because your app keeps evolving, you have to show different things, right? And that's what we just did with a Cassandra query language, but connecting to the same cluster, right? No difference, right? I'm now connecting to the same cluster, and as a database, I can interact with it using the Redis CLI, which tells me, give me the top 10 books sorted by the number of stars they got, the total rating, the highest rated books, right? And with the scores, like with the ratings. Or give me the top 10 books with the maximum reviews, because these are the pages that you keep throwing up, and these pages keep changing. And you can write into Redis and query from Redis, and at the same time write into Cassandra and query from it. Please, yeah.
This is the same product table with both column in Cassandra format, also number of reviews in Redis.
No, it's not. So the question was, is this table the same product table that was there on the Cassandra side? And the answer is no, it's not. These are 2 different tables internally, but they're both persisted with strong consistency. So you will be able to write to Redis and to Cassandra. What you would have traditionally done is you would have written to Cassandra for one step or SQL for one type of data. The other type, you would keep it in memory in Redis, and you would have figured out another place to persist the underlying data for Redis. So if Redis dies, you can go read it from there and repopulate it, right? And Redis is a different DB, Cassandra or SQL is a different DB, and you'll have a third DB. When you do a backup, you'll have to figure out all of this stuff. In this case, you just write into one database. It'll give you the data back using all the different APIs. The backups and all are taken care of.
But underneath, you actually use a different like a mechanism to store it.
We use a different format, but the files are in the similar format that the core database understands. So the core database is the same. It has different API layers on top. So think of it as Yugabyte tables at the core. There's a different Yugabyte table for Cassandra products, and there's a different Yugabyte table for Redis. And they both store data, they both write data into the underlying DocDB in a common format. But they will lay data out the way they want, because the way it is optimal for Redis and Cassandra.
So in case the node fails, how long you can reconstruct it? Because of
Great question. So in case a node fails, what is the reconstruction time? So let's split that into two parts, right? A node fails, how will my queries be affected, right? That question is, if a node fails, only the tablets that have leaders on that node will get affected, but in a matter of seconds, right? Which is a configurable value, but currently it's like a few seconds, 2 to 3 seconds. You will have new guys serving the values. So so if you have 3 nodes, so let's take a 3-node example, right? But each of the nodes are replicated. Each of the pieces of data is replicated 3 ways. And each of the pieces of data is in a raft group. So the minute a node dies in a few seconds, like in 2, 3 seconds, the next guy will take over as the leader and start serving. And the client is smart enough to know this guy died. Let me go find the new leader and serve the data. So your app is not affected, right?
But you need to have the fourth node, right?
If you, yeah, we'll get to that. Yeah, that's a great, yeah. So if you don't have a 4th node, you can't do much, right? But let's say you had 4 nodes with replication factor of 3. If a node fails, there's a configurable timeout. We wait for the node to come back. We don't do anything, right? Because you don't want to simply do unnecessary work. That configurable timeout is 5 minutes at this point. After 5 minutes, we'll automatically re-replicate its data to an existing node, if there is one.
Yeah. The replication will take more than 3 seconds.
The replication will go on in the background. Your foreground queries are not affected. Your app is still running. He's asking me to speed up, but I will take your question. Just give me 1 second. So the other thing I wanted to show you guys is the load as users, or the Bangladeshi click farm for those of you who see Silicon Valley. So, so there you go, farm activated, right? So now we can go and see what's going on in the database. So the minute I did a refresh, what you see is that the reads and writes start getting scattered across to different nodes, right? So, and depending on the app and the type of keys, you'll see that the load and the distributions will vary, right? So, and one of the things that I would also like to do is we can actually scale the number of replica sets on the fly. So we'll be able to just add like a new guy, right? So it's pending, creating. Well, it'll come up soon enough. Yeah, so I'll keep going to finish, but I'll come back and show you guys it's done. Oh, it's done. So what you notice is that a new node just got added to the system, right? And the new node is now, so at Yugabyte, we're all about running in production, right? So we won't like go and rush into copying all the data. You can throttle how slowly you want the new node to start taking data. So it's going to happen in the background in a way that your app should not get affected. That's the most important thing, right? So what you'll notice is that, like, if you look at the number of shards, right? You have a certain number of shards, and you're seeing that the load is slowly getting moved to the new node, while the data is being served by all the other guys. So if I refresh, you'll see that more shards slowly start moving, and the data gets copied. The node now comes into the system. It starts serving data, and all of this is online, right? I mean, we can wait for it to finish, but I think you'll probably kill me. So, so let's, yeah. So our database is Apache 2.0. It's in the open source. We'd love for you guys to get involved. Like, it's C++, but hey, it's still a good language. So It's highly performant. So, but anyways, download it, try it. You can play with a lot of failure scenarios on your laptop. We have an explore section that talks about how automatic sharding works, how we can do load balancing automatically, how we do distributed transactions. So you guys can download it as a Kubernetes or like a binary or however, and try it out on your laptop. Watch us, stars, and follow us on GitHub. We'd love for you guys to try it out to help us out. Yeah, I think I said that already. So that's all I had. I think there was a question that you had, yeah.
The question was, to serve the reads, it can go to any of the follower node, right? Or does it have to go to the leader?
There's multiple modes. It's a great question. We offer tunable consistency. So if you want to treat it as a database, it has to go to the leader node because that's just the way it works. But if you want to read from a follower, we allow that option. And you can also optionally read from the follower in the nearest data center to the app. So
I have one more question. So what is the data overhead? Let's say I want to store 1 gig of data. And what is the storage bloat that happens?
This is okay. So this is yeah, it depends on a lot, but I'll tell you a slightly different way. We do prefix compression for the data in memory, and then we recompress it using, on top of the prefix compression, we do snappy compression and store it in disk. So it's pretty well compressed, but that's a hard question to answer because, yeah. Yeah, please, yeah. It's a modified RocksDB. So in the sense, we have taken out RocksDB's write-ahead log. We took out RocksDB's MVCC. We integrated RocksDB with our Raft log as the source of truth, like for starters, and a lot of other changes. So.
But it's still a level DB fork, so it still has very large write-ins.
Yeah, so his question is it a RocksDB at the bottom? And the second follow-up question was, it's still a level DB fork, so it has a very large write amplification. We have changed the way the compactions work based on our HBase learnings. So we actually do a size-tiered compaction. So we try to strike a trade-off between size amplification and number of rewrites, right? So and today's systems, I/O is the bigger bottleneck than raw disk size, right? But there's I mean, the answer also is not that straightforward because like it's not a single tablet in a machine. Like suppose you have 500 gigs of data in a machine. If it's a very simple single shard system, you'd need another 500 gigs of data to do compaction, so you can only do 50%. But we do sharding inside, so it's really like the 500 gigs divided by the number of shards divided. So there's a whole bunch of computations which decreases the size amp.
Hi,
Yeah.
I just wanted to ask, like, since you're strongly consistent and also geo-distributed, do you support SQL joins?
A great question. So it's in our roadmap, but here's our main thing with joins. As you add nodes, your join performance could get worse for the wrong kind of join, right? So this is the one sticking point that a lot of companies like Facebook, for example, has an entire SQL tier. They don't do joins. They don't do cross-node joins, right? But they try to place data in such a way that your data that you want to join comes together, which was the co-partition table kind of example. So yes, we will support it eventually, but right now we don't because we feel it is very difficult to tell an end user at what point does your join get worse with node addition, because you add nodes to make it better, not worse. So.
What kind of assumptions do you make about storage, and how do you qualify what is the parameters that you require for good performance and transactional consistency?
Great, yeah. So we assume that so the question was, what kind of assumptions does Yugabyte make about storage, and what do we qualify for performance, right? How do we qualify it for performance? For transactional consistency, yeah. So we assume we run on top of a file system. We typically recommend XFS because we have a lot of experience with it, but any file system will do. We assume that the file system has sync support, so we are able to store data, like et cetera, right? At the core, we assume that you have a SSD type device because SSD is the norm now. We're not like, still designing for the hard disk age. That said, however, we have enough architectural depth inside Yugabyte to enable tiering of data to hard disk-like tiers automatically, like in the background. So you will still be able to move older, colder data to cheaper tiers, but keep your hot data in the serving tier, right? So, and now as far as transactions go, it's a split. Like distributed transactions depend on clock skew. Single row transactions depend on your network as well. So It's not just storage. So from a storage perspective, we just require SSDs, and the faster it is, the faster you get. But at a certain point, it'll be diminishing returns because these other guys will take over. Sure. Oh, yeah. So, yeah, I think one point that Kannan was mentioning is that we don't depend on software rate, so we can just use JBOD, like just disks, just a bunch of disks. So. More questions, guys?
All right.
I've got stickers. I forgot to hand them out to all the people who asked good questions, but please do. Yeah, they're in the back as well, apparently. So please do stop by, say hi, and yeah. Thank you. Thanks for